All right, today's video deals with a little bit of what we talked about yesterday about KSP, and it also involves what's called the common ion effect. Okay, the common ion effect, actually, if we come back up to one of our previous examples right here, letter C in this example from the previous video is an example of the common ion effect. For example, in this problem, it was XF2 in equilibrium with X2 plus and 2F minuses. Okay, and what happened here is instead of dissolving it in water, they dissolved it in NaF. And NaF, because it is an alkali metal, is going to break apart into Na plus and F minus. So instead of dissolving it in water, you're dissolving it in a solution that already has some fluoride ions in it. And see how XF2, which breaks apart into X2 plus and F minus, and NaF have an ion in common. They both have F minus in it. That's the common ion effect. Okay, and what happened with the common ion effect is when you dissolved it in F minus rather than water, by increasing this, it caused the reaction to shift to the left, and that makes XF2 less soluble. Okay, and that's what a common ion does. It's what a common ion always does, is it causes that reaction to shift back to the left and makes that insoluble salt even less soluble. So, if a solution contains two dissolved substances that share a common ion, okay, so let's look at it here, AgCl. So AgCl dissociates into Ag plus and Cl minus. So if you're dissolving it in something other than water, say some potassium chloride or some AgNO3, anything that has something that's going to be soluble in it, you're going to produce chloride ions. Well, that would be the common ion, would be Cl minus. In silver nitrate, the common ion would be, you get Ag plus and NO3 minus. So the common ion would be Ag plus. Anytime you have a common ion, the reaction will shift back to the left and decrease the solubility of that compound. Okay, so let's look at some examples of this. So the KSP of silver chloride is 1.58 times 10 to the minus 10th. What's the molar solubility in water? So here we have just a regular AgCl, which is a solid in equilibrium with Ag plus aqueous and Cl minus aqueous. So this is going to be X, this is going to be X. So 1.58 times 10 to the minus 10th is going to equal X squared. So we just have to take the square root of 1.58 times 10 to the minus 10th. And we get an X value, which is equal to the solubility. Remember, the solubility means the X value of 1.26 times 10 to the minus 5th. Okay, and now we're going to start doing some problems with some common ions. Okay, what happens if instead of pure water, it's dissolved in has a silver ion concentration of 5.5 times 10 to the minus 3rd. Okay, so that means that this, rather than being X, is now 5.5 times 10 to the minus 3rd. So now we've got 1.58 times 10 to the minus 10th is equal to 5.5 times 10 to the minus 3rd. And now we've still got our X value here. Okay, so really now the only thing we have to do to solve for X is divide. So we're going to take 1.58 times 10 to the negative 10th divided by 5.5 times 10 to the minus 3rd. And I get 2.87, not negative, that's not a negative, 2.87 times 10 to the negative 8th. What happened to the solubility of AgCl when we added a common ion? It was 1.26 times 10 to the minus 5th, and now it's 2.87 times 10 to the negative 8th. Much, much less soluble once we add that common ion. Okay, letter C says a 0.025 molar KCl solution. Again, we don't care about the K as much, but now that means the chloride ion concentration is 0.025. So once again, 1.58 times 10 to the negative 10th is going to equal, now the common ion isn't the silver, it's the chloride. So now we're going to have X times 0.025 is the Cl minus concentration is what we put in there from that potassium chloride. So once again, 1.58 times 10 to the negative 10th divided by 0.025 equals the X value, the solubility is 6.32 times 10 to the negative 9th. Notice that in both cases, the addition of the common ion caused the reaction to shift back to the left, because in both cases we can see that the solubility in water only is to the negative 5th, but when you add a common ion, it's much, much less soluble. Okay, so one more example here. So propanoic acid, a weak acid. Write the chemical equation for the dissociation of propanoic acid. Notice that COOH at the end. That's what tells you that's an acid, other than obviously they tell you. But remember, it's this hydrogen on the end that's the acidic hydrogen. So when you put that into water, you're going to get CH3, CH2, COOH in equilibrium with CH3, CH2, COO minus plus H plus. Again, you can include the water in there or not. Okay, and then part B, write the equilibrium constant expression. Again, don't let the fact that this isn't a KSP situation. This is an acid that's aqueous. That's why I put that in there. Okay, it has to be a solid for it to be a KSP situation. So the equilibrium constant expression is going to be the concentration of CH3, CH2, COO minus times the concentration of H plus over the concentration of CH3, CH2, COOH. Okay, and then part C says 0.010 moles of potassium propanoate is added to 150 milliliters of a 0.20 molar solution of propanoic acid. Calculate the pH of the solution. So again, potassium propanoate means you're adding some of that conjugate base. Oh, this is a common ion situation. Again, it's going to cause that reaction to shift back to the left. Okay, so the concentration of the acid is 0.20. Okay, the concentration of the propanoate ion, we don't know, but we do know the moles and we know the volume. Okay, so the Ka is 1.34 times 10 to the minus 5th. So 1.34 times 10 to the minus 5th is going to equal the propanoate ion concentration, which again, let's just figure out what that is. 0.010 divided by 0.150 is the volume, equals a concentration of 0.0667, and that's times the hydrogen ion concentration, which we don't know. So we'll just call it, instead of H plus, we'll just call it X. Okay, but we know that it is the hydrogen ion concentration, and all of that's going to be over the concentration of the acid, 0.20. Okay, so we're going to multiply this to get to that. We're going to divide that. So we're going to take 1.34 times 10 to the minus 5th times 0.20 divided by 0.0667. And again, that tells me the hydrogen ion concentration is equal to 4.02 times 10 to the minus 5th. And then the pH just equals the negative log of that number. So negative log of that answer equals 4.40 would be the pH. All right, last one, letter D. 50 milliliters of 0.16 molar HBr is added to 50 milliliters of 0.4 molar, so of the acid, propanoic acid. Calculate the concentration of the ion, of the conjugate base ion in the resulting solution. So again, we've got the same equation as we had before. we've still got the same Ka value, 1.34 times 10 to the minus fifth is going to equal, and just go through it one by one here, guys. Okay, the first one is, what's the concentration of the conjugate base? Okay, well, that's what they're asking us for. Calculate the concentration of the conjugate base. So that we're going to put X in for that. Okay, what is the hydrogen ion concentration? Well, we've got HBr, and that's a strong acid. You got to know that. That breaks apart completely. So it was 0.16 molar HBr, but that's when we had 50 milliliters. Now we've got 50 milliliters plus another 50 milliliters is 100 milliliters. So we're going to double that volume, which reduces our concentration by half. So 0.16 divided by 2 equals 0.08. Okay, so that's our concentration of H+. And then the same thing happens with the concentration of the acid. It was 50 milliliters, but now by combining those two, it's 100. So that one's also going to get reduced by half to 0.20. Okay, notice we didn't have to do that up here in part C because they said you added 0.010 moles of potassium propanoate, but there wasn't any volume change. You didn't add a certain volume of something. You just added some moles, which theoretically didn't change the volume. But in D, because you had 50 milliliters and 50 milliliters and you put them together, you've now got 100 milliliters of solution. Okay, so 1.34 times 10 to the minus fifth again, times 0.20 divided by 0.08 is X, which is equal to the concentration of the propanoate ion is 3.35 times 10 to the minus fifth. Okay, so notice that in every case, anytime you have the case of a common ion, that's always going to cause that reaction to shift back to that left-hand side. And it's going to shift to that left-hand side, which reduces the solubility of the acid or the insoluble AgCl or any other compound. Anytime you add a common ion to that, it's going to cause that reaction to shift back to the left, thereby reducing the solubility of that compound.